We actually know a considerable amount about physics now, even though we've only talked about some of the very early discoveries in relation to the nature of motion. But what I want to do before we move on to look at Galileo's second really significant discovery that set the foundations for what Einstein would later do, I want to talk about some of the problems that we can actually solve now and some of the understanding that we have from the work that Galileo did on the nature of motion, which was followed up by Newton and formalized by Newton. Aristotle had the view that a moving object must be propelled by a steady force in order to keep it moving, that otherwise it would seek its natural state of motion, which for most things Aristotle had the view was in fact a stationary state. So, for example, with something like a cart that was being pushed by somebody, that person was applying to it a force, and that because they were applying a force to it, it made the object move, made the cart move forward at some particular velocity. Let's suppose that this steady force being applied to the cart made the velocity of the cart be about 1 meter per second, so about a walking speed. If the person then ceases to push on the cart, Aristotle had the view that the cart would eventually come to rest. Sometime later, after the force was taken away, that the speed would drop to some smaller value. Let's suppose it would drop to around 0.5 meter per second, and that finally, unless the force was returned to the cart to keep it going, that the cart would come to rest and not be in motion at all. And this, of course, agreed very accurately with what Aristotle and everybody observed and what we observe today in the world around us. Galileo, however, would have had a different opinion about what was going on with this cart. Galileo understood that friction played a significant part in the subsequent motion of the cart, something that Aristotle had no concept about. So we've got the cart initially with a force applied to it by somebody pushing on the cart, and they get the cart moving in the same way as in our previous example. They get it moving at about a walking pace of about 1 meter per second, about 3 kilometers per hour. But in this case, Newton would say that there is another force acting on it. And the force that Newton would identify and Galileo would identify as acting on this cart is a force of friction. They would say that there was friction in the axles, in the wheels of the cart. They would say there was friction with the ground. Imagine the ground was very, very rough. You would obviously find it much more difficult to push the cart than if it was on a very smooth surface. And that this friction force is acting opposite to the direction of motion of the cart. And for as long as the cart moves, this friction force is acting on the cart. And so both Galileo and Newton would say that once the driving force had been removed, once the person had stopped pushing the cart, of course the cart will slow down. Not because it's its natural state to be stationary. They would say that while the cart is moving, while it's rolling along, it's suffering a force of friction from the ground and in the axles of the wheels, and that this force eventually brings the cart to rest. And the point at which the cart comes to rest, that is the only point at which a force of friction disappears and no longer exists. It's only when the cart is actually stationary that this force of friction has gone completely. This was quite a leap, though, for Galileo to make in terms of describing the state of motion of moving objects. His understanding that friction acts on all moving objects and eventually brings them to rest. That is, it stops them from moving. That is the reason we see the motions of objects that we see in the modern world. The property of objects to resist changes in their state of motion in the absence of either a driving force that's pushing it or a friction force that's acting to bring it to rest. The tendency of an object to keep moving, if it's already moving, is what Galileo called inertia. And it was the first time that anyone had this idea about the true nature of what keeps objects in motion. Isaac Newton, he refined Galileo's ideas into the first law of motion, and you'll remember that Newton did this about a little over 20 years after the death of Galileo. Newton was born just a short time after the death of Galileo, and in his early 20s is when Newton refined these ideas about the state of motion. And Newton agreed with Galileo on the basic nature of how things moved. Newton wrote in his book, which is often called the Principia, but its English translation is actually the Mathematical Principles of Natural Philosophy. Natural philosophy is the very old name used for physics. In some very old universities, you will still see on the walls of the physics department the words, the Department of Natural Philosophy. Natural philosophy is what developed into our modern idea of physics. Newton wrote in the Principia essentially these words, that every object continues in a state of rest or uniform speed in a straight line unless acted on by a non-zero net force. Simply put, he was saying that unless a force acted on an object to change its state of motion, the object simply would not change its state of motion. And whenever we see objects moving and slowing down, which we see all the time, Newton and Galileo would say, well, these objects, even though it might appear that they're moving without any force acting on them, that is not true, that a force is actually acting on them. This definition that Newton wrote, the key word is continues. If an object is at rest, Newton and Galileo would say it will remain at rest. If the object is moving, both Newton and Galileo would say it will continue to move in a straight line unless, and the unless is the key point here, of course, unless it is acted on by a force to change its state of motion. Now, this was a profoundly different understanding to motion than Aristotle had, and it is one that we know to be an accurate assessment of how things move today. I'd like to look now at a number of different problems for you to solve related to just this notion of inertia, this notion that objects continue to do what they're doing unless they're acted on by a force, because we can actually solve some very difficult problems in physics and our everyday life by applying Newton's first law to the problems that we will have a look at. The first one is a problem about a hockey puck. A hockey puck is what hockey players use to hit around on the ice, and we're using this example because friction is quite low between objects and ice. Things tend to slide quite long distances on ice, whereas on other surfaces they won't. Our question says this: the hockey puck slides across the ice and eventually comes to rest. And the question asks, how would Aristotle have explained this observation, and how would Galileo and Newton explain it? Here's our situation. We've got a hockey puck that's moving across the ice at 5 meters per second, and eventually this hockey puck, if our slab of ice is long enough, will come to rest and have a zero velocity. And the question that we're asking here is, how would Aristotle describe this situation, and how would Newton and Galileo describe it? Well, Aristotle would say that the natural state of something like a hockey puck, because it's constructed of things from the Earth, would be stationary, like the Earth. The Earth, he believed, was also stationary, and that was the natural state of things. So he would say that once the hockey stick had stopped pushing the hockey puck across the ice, once that force had left it, that it would eventually come to rest. Aristotle would have some problem explaining why, after the puck was hit by the hockey stick, why it actually continued to move. He would have had to explain it by saying that air rushed in behind the hockey puck to push it along. But he would have some difficulty in then explaining, well, why does it actually come to rest then? Why did the air stop rushing in behind it? Nevertheless, that's what Aristotle would have said about it, that the natural state of the puck was at rest, and once no force applied to it, it would eventually come to a halt. Galileo and Newton, on the other hand, they would have said that, well, yes, the hockey puck is sliding across the ice and there is not much force on it, but they would have said there is some force on it. They would have said that there is a force of friction acting on the hockey puck while it's moving, and that this friction force, although it's not big on ice, this friction force would eventually lead the hockey puck to come to rest, at which point the friction would stop. Only a moving object suffers this friction between itself and the surface. When it comes to rest, this horizontal friction force disappears. And any tendency to make this puck move again, of course, will bring back the friction force until it starts to slide. Therefore, Galileo and Newton would have realized that the reason the puck comes to rest eventually is because of this friction between the puck and the ice. This friction force is very small, of course, on the surface of the ice, but it is not, in fact, zero. There is still some force there. If the puck was sliding across a wooden surface or a concrete surface, then the force would be much greater and the puck would come to rest much sooner in that case. Let's look at another question. Let's look this time at a question to do with the universe. Let's suppose that we're considering the motion of galaxies. Galaxies are known to be moving in the universe, not just from the expansion of the universe, but they're known to be moving in a motion separate to the actual expansion of the physical space of the universe. If a galaxy is so far away from other galaxies that it feels no appreciable gravitational force, it feels no significant gravitational force from any other galaxy, the question is, what keeps the galaxy moving? What makes it move if it's not suffering any force? Now, we know that what happened originally in the creation of the universe was the Big Bang that took place, that gave rise to most of the physical things that we see in the universe. And it also gave motion to objects away from each other. So we have clouds of gases and particles originally, just pure energy in the first instance, that gradually turned into particles and then into atoms and so on. All of these objects were moving away, given some velocity by the initial explosion of the Big Bang, just by a conservation of momentum notions. If some objects are moving in one direction, other objects must move in other directions. So we've got these particles moving away, and of course we do have a gravitational attraction of these particles inside the gas clouds, so that eventually what we see happen is that the gravitational attraction inside the gas clouds make the gas clouds become smaller and smaller, and the motions of particles in the gas clouds eventually lead to, in fact, a rotational motion of the cloud, although we don't have to be concerned about this. What we're concerned about is this green arrow, which is the outward motion of the cloud of gas and particles, which eventually forms by gravitational attraction into a galaxy. Now, if we understand the first law of motion correctly, then what we understand is that unless these clouds of gases and particles are acted on by some other force, they will just continue to keep on moving. And in our problem, we've said that this galaxy is so far away from other galaxies that it feels no significant gravitational force from any other object, then it feels no force at all, and therefore it just keeps moving. No force is necessary to keep it moving. That's the point. That's the point of Newton's first law. If the object is moving to begin with, it won't change its state of motion unless it's acted on by some other force. And this is as true for the planets and for galaxies as it is true for the cart and the hockey puck that we've just been talking about. According to Galileo and Newton, once the Big Bang explosion had brought all matter into existence and started things moving. The only thing that can change the motion of the object later on is the existence of some other force to prevent it moving. Galaxies, I've just explained, are formed over time by the gravitational attraction between the particles, subsequently the stars that make up these galaxies. But the total motion of the cloud of gas and all of the stars and particles that form the galaxy, the total motion of this galaxy requires no force to keep it moving. What about friction, you might ask, in space? Well, friction is a negligible force in space. Friction does exist. It comes from the existence of protons that things can crash into in outer space. There is approximately 1 proton in every cubic centimetre of outer space. So the friction is very small in outer space and therefore has no effect on the motion of objects through space. We will talk next time about some more problems that involve inertia and the motion of objects to see if we can gain a better understanding of what is going on with these very basic notions of how things move.